The purpose of all standard training algorithms is to set the network weights. Before explaining how this is done though, let's address a point I've made in the last couple of videos, that the Hopfield network has a memory. To see what this means, let's compare what a backpropagation feed-forward network does with a Hopfield network. This is shown on the diagram on the screen. We can see from this that a feed-forward network is trained to produce a target output when it sees the correct input pattern. However, a Hopfield network is trained to reproduce the same pattern at its outputs that it receives at its inputs. At first sight, this seems useless, until we remember that networks can handle noisy data. So even if there's a corrupted pattern at the input, the network can reconstruct the perfect one at its output. In this way, it has a memory of the perfect pattern stored in its weights, which can be recalled when an imperfect one is input, just as we can picture someone's face from a memory when we get a glimpse of them. Because the network associates a perfect pattern with a corrupted version, it is sometimes called auto-associative. As a slight aside, we can also add a second layer to the Hopfield structure, and by doing this we can associate one pattern with a different pattern. In other words, we put in a particular pattern and the network responds with a different one. Such a structure is called a bidirectional associative memory, or BAM, and this type of memory is also sometimes referred to as heteroassociative. So let's see how we actually train the Hopfield net. We'll do this using an example. Let's say that we have a two-input network and we wish to train this with two patterns as shown on the screen. The two patterns are labeled A and B, and the two pixels are labeled pixel 1 and pixel 2. Now, firstly, we know from the last video that W11 and W22 must be equal to 0. So we can set these straight away. Also, W12 must equal W21, and so we only actually need to calculate one of these. The training works like this. Take each pattern in turn, and for the corresponding weight indexes of the weight you're trying to calculate, multiply the two pixel values together which correspond to these weight indexes and add all these contributions up. So in our example, where O is the required output, we have a formula shown on the screen. Remember that in a Hopfield net, a 1 corresponds to a filled-in pixel and a -1 to a blank one. And so the network is as shown on the screen. And we can write down this formula conveniently as shown just below. Now, if we input corrupted versions of these two patterns, the network should respond with the correct versions after relaxing. Of course, you can't train more than a few patterns or the network will start getting them wrong. And in reality, the network can get temperamental and some patterns may not train properly. Notice how this training method uses just a single level of calculation and is not iterative like backpropagation. Because Hopfield was a physicist, he actually wrote down the current state of a network as an energy function, and you can look up the formula for this in a book if you like. And in fact, each pattern corresponds to a dip in this energy function, and we set this dip by training the pattern. The network then settles in the closest energy dip to the starting state as it relaxes. So although the Hopfield net is a bit esoteric, it shows us clearly how a recurrent network can have a memory. I realize that the training example I've given here is probably a little bit difficult to follow, so in the next video I'll give another training example of a Hopfield net to further illustrate exactly how it's trained.